Hello again. In this topic, we're going to take a look at what's called the chain rule, which is going to help us to calculate derivatives of composite functions. Let's start with a basic example to understand what we're talking about here. So for example, we have here the function x squared to the 10th power. This is a composite function because I have, in a sense, a function x squared being raised to the 10th power. And so we want to learn how to find the derivative of this function and functions like it. Well, let's just suppose that it follows the power rule that we've learned so far. And so if I just sort of think, okay, well, I have this quantity to the 10th power. Maybe the derivative is so f prime of x, maybe the derivative is just 10 times x squared to the 9th power. I'm going to put a question mark there because I'm really not sure about this yet. Well, one way to check this would be to use some algebra to expand this first. We know that from algebra, we know that x to the second to the 10th power, if we raise a power to a power, we've learned that we're supposed to leave the base alone and multiply the exponents. So that means that another way to write f of x would be x to the 20th power. Well, that's easy to differentiate. F prime of x is 20 times x to the 19th. Now, if we use the same idea here, and we look at this 10 times x squared to the 9th, then that's equivalent to writing 10 times x to the 18th. Now, obviously, these two expressions, right, this 10x to the 18th, is not equal to 20x to the 19th. So obviously, we've done something wrong. Now, I'm pretty confident that the second version is right. I know my rules for algebra, and I know that the rules that we've learned so far work. So there must be something wrong with what I did over here on the left. There must be something wrong with the 10x to the 18th. All right, well, what could we do to make the expression on the left equal to the expression on the right? And if we look at this, well, to make the 10 turn into a 20, I could multiply by 2, and x to the 18th times x is x to the 19th. And now, if we look at this carefully, if we look at that 2x carefully, we should notice that it's the derivative of x squared. And that should be interesting, that the 2x is the derivative of the x squared. And it turns out that that's the basis for what's called the chain rule. So a correct way to calculate the derivative of the function x squared to the 10th would be like this. If f of x is x squared to the 10th, we can start off by saying that the derivative is 10 times x squared to the 9th, but then we need to multiply that by the derivative with respect to x of the x squared. And so then this tells us then that the derivative, f prime of x, is 10 times x squared to the 9th times 2x, which, if we go through the algebraic simplifications, is 20x to the 19th. And so that works out. Now, this is not a proof of the chain rule. This is just an example of it. The proof of the chain rule is, I think it's beyond what we need for this course, so I'm not going to go through a proof of it. If you're interested in a proof of the chain rule, please feel free to look it up using your favorite web search. I won't prove it here. All right, so here's a statement of the chain rule. So if we're taking the derivative with respect to x of a composite function, so notice the composite function notation here that you learned back in an algebra course, f of g of x. The chain rule says that if we have a composite function, f of g of x, and we're differentiating with respect to x, that it tells us what we do is we calculate the derivative. We calculate f prime, the derivative of the outer function, at the inner function. We leave the inside alone. But then we have to multiply that by the derivative of the inside function, the g prime of x. And so that's what we really did in this previous exercise. If we think of this as the outside function being something to the 10th power, right? We had something to the 10th power. And what did we do? We calculated 10 times the something to the 9th power, and then we calculated the derivative of that same something. In this case, it was x squared. Now, there is an alternate notation for the chain rule that we need to be aware of. Here's what it says. It says, if y is some function of u, right? So instead of x, let's make it a function of u. Then dy dx. Now notice I'm calculating the derivative with respect to x, but f is a function of u. Okay, so be very careful about this. So then dy dx would be the derivative of y with respect to u times the derivative of u with respect to x. Now, let's see this in terms of the exercise we just did. All right, so here we had the function. Here we had the function x squared to the 10th power. In a sense, that's the same as u to the 10th power, where u is equal to x squared. That's an alternate way to write that. F of x is x squared to the 10th. That's the same as u to the 10th power, where u is x squared. So then the derivative, f prime of x, would be 10u to the 9th. The dy du, the derivative with respect to u, times 2x, the derivative of u with respect to x. Now, u is again x squared. So again, that's 10 by x squared to the 9th by 2x, which is the same result, 20x to the 19th. So that's another way that we can think of the chain rule is in the differential notation. It's an important way to think of it. You see this notation frequently in later courses. All right, but in the way I teach this, though, I'm going to tend to think of this box idea. I like to teach this with the idea of thinking of the composite function and thinking of the inside as a box, and then thinking of the derivative in terms of the box, and then doing some substitutions. All right, so let's see some examples. We're going to just now get some practice differentiating. All right, so here we're asked to differentiate each function. We've got 3 functions here. Let's just take a look at the first one. So here I have f of t is 6t minus 7 raised to the 5th power. So here's how I see this. I see this as a composite function, and I have box raised to the 5th power. All right, 6t minus 7, that's the inside. All right, that's the composite part. So what's going to happen here is if I wanted f prime of t, that would be 5 times box to the 4th. And then I need the derivative with respect to t of the box. All right, now what's in that box? Well, that box is 6t minus 7. That box is 6t minus 7. All right, so then that means that f prime of t is 5 times the quantity 6t minus 7 to the 5th power. Now the derivative with respect to t of 6t minus 7 is just 6. So that I'm just using rules that I've learned in the past. All right, now what I would do from here is simplify this a little bit. We can easily combine the 5 and the 6 because they're factors. 5 times 6 is 30. So I would write that f prime of t is 30 times 6t minus 7 to the 5th power. Now I cannot distribute that 30 inside the quantity because that quantity is being raised to the 5th power, and we would have to take care of any exponentiations before multiplications if we're following the rules, the standard order of operations. So let's leave it like that. All right, now r of p is sine cubed of p. Okay, now remember that this is the same as writing sine of p raised to the 3rd power. And so now, if I think of this as a composite function where I'm raising box to the 3rd power. Okay, and again, I'm going to think of the box as sine p. So then r prime of p would be 3 times whatever's in the box to the 2nd power times the derivative with respect to p of whatever's in the box. And again, what's in the box here? Sine p. Sine p. All right, so then r prime of p is 3, and sine of p square, again, we can write that as sine square p. And then the derivative of the sine function, the derivative of sine p, is cosine p. So that's what I would write. R prime of p is 3 sine square p, cosine p. H of x is the cube root of 5x squared minus 4. Recall that if we think of what a cube root means, and we remember that that's the same as writing a specific type of power expression. This is the same as writing the quantity 5x squared minus 4 to the 1/3 power. Why don't you try to take this one from here and calculate its derivative? All right, so again, what I see from this is I have a box, 5x squared minus 4, raised to the 1/3 power. All right, so then applying what I know and the chain rule, that would be 1/3 box to the negative 2/3 power from the power rule times the derivative with respect to x of whatever's in the box. All right, and then again, what's in the box? 5x squared minus 4, 5x squared minus 4. All right, so that's 1/3 times 5x squared minus 4 to the negative 2/3 power, and then the derivative of 5x squared minus 4 is 10x minus 0, or simply 10x. All right, and then if we wanted to clean this up a little bit, there's a couple different ways we could write this. H prime of x, again, I would combine the factors. 1/3 is being multiplied by 10, so I could certainly write that as a 10/3. I would bring the x up front 10/3 x, and then I'd have the 5x squared minus 4 to the negative 2/3 power. If we wanted to write this as a fraction, remembering that a negative exponent means a positive exponent in the denominator, we could do something like this. We could write this as 10x over 3. And then we could even take care of that 2/3 power. That means we have a cube root of the quantity square. So we have 3 times the cube root of 5x squared minus 4 squared. So that's a couple different ways we could write this expression. All right, so here's a few more expressions. And what I would recommend is that you pause and try these on your own. Calculate the derivative of each of these functions. All right, so our first function here, f of t, is the sine of the cosine of t. So here I'm taking the sine of box. All right, so then the derivative, f prime of t. Now the derivative of the sine function is the cosine function. So I'd have the cosine of whatever's in the box times the derivative with respect to t of whatever's in the box. So I'd have the cosine of cosine t times the derivative with respect to t of cosine t. So then I'd have that f prime of t is cosine of t times the derivative with respect to t of cosine t is negative sine t. And so what I would do here is maybe bring that negative factor out front. I would write f prime of t is negative cosine of cosine t times sine t. M of q is 45e to the negative q squared. All right, the 45 is just a constant multiple. It's not going to have too much bearing on the derivative. We just kind of carry that along. But what's in the box here, if we want to think of that idea? And so here, I know how to take the derivative of e to a power. We've learned how to do that. And so the power is the box in this sense. So then m prime of q is 45 times e to the box times the derivative with respect to q of whatever's in the box. In this case, what's in the box? Negative q squared, negative q squared. So then m prime of q is 45 e to the negative q squared. And then the derivative of negative q squared with respect to q is negative 2q. And again, what I would do here is clean this up a little bit. 45 times negative 2q, I would bring that forward. So I would write m prime of q is negative 90q e to the negative q squared. That's what I would write. S of x is the natural log of 7x squared. So I look at this as the natural log of the quantity, the box, is 7x squared. All right, differentiating the natural log function, s prime of x. The derivative of the natural log function is 1 over x. Well, it's not x, it's 1 over box. 1 over box times the derivative with respect to x of box. And in this case, what's in the box? 7x squared, 7x squared. So s prime of x is 1 over 7x squared. The derivative of 7x squared is 14x. So that's 14x over 7x squared, and we can simplify that. That's 2 over x. Now actually, we didn't need to use the chain rule for this one. An alternate approach would have been to start by using rules for logarithms that we learned back in algebra. So s of x is the natural log of 7x squared. Recall that that's the same as writing the natural log of 7 plus the natural log of x squared, using a property for logarithms, and using another property for logarithms, that's the natural log of 7 plus 2 times the natural log of x. And we could have differentiated from there. So then s prime of x, the natural log of 7 is a constant, and so its derivative then is 0, plus 2 times the derivative of the natural log of x is 1 over x. So I have 0 plus 2 times 1 over x, which is 2 over x. So we need to be aware of our rules for for logarithms and exponents. But your rules for logarithms can be helpful if we need to calculate derivatives. All right, here's a few more examples involving some trigonometric functions. Now would be a good time to pause and try these out on your own. All right, so here I have that y is the secant of 4t minus 1, if I'm going to think of that 4t minus 1 as the box. All right, so now the derivative of the secant, let's see, the derivative of secant x with respect to x was secant x tangent x. So the derivative of secant box is going to be, so then y prime is going to be differentiating with respect to t, secant box tangent box times the derivative with respect to t of what's in the box. And what's in the box is, again, 4t minus 1 here. Now, the derivative with respect to t of 4t minus 1 is just 4. So I would write that y prime is 4 secant 4t minus 1 tangent 4t minus 1. All right, here we're asked to differentiate g of x as the cosine of the square root of x. So that's the cosine of x to the 1/2 power. So I'm going to think of that x to the 1/2 power, that's what's in the box for this expression. Then g prime of x would be negative sine of whatever's in the box times the derivative with respect to x of whatever's in the box. So negative sine of x to the 1/2 power, or the square root of x, and then the derivative with respect to x of x to the 1/2 power. So then g prime of x is negative sine of x to the 1/2 power, and then the derivative of x to the 1/2 power is 1/2 x to the negative 1/2, just using the power rule that we've learned. All right, and let's clean this up and maybe put it back in terms of radicals, and I'm just going to write this as a fraction. Remember that x to the negative 1/2, that would be the a square root of x in the denominator. So I'll write g prime of x as negative sine of the square root of x over 2 times the square root of x. All right, and then we have tangent fifth of 4 theta. Now this was a little trickier. Let's see, so this is the same as writing the tangent of 4 theta all raised to the 5th power. And so now if we look at this expression, it's actually multiply composite, right? We have something raised to the 5th power, but on the inside we're also taking the tangent of something. All right, so this one's a little tougher. Let's start by thinking of this as something to the 5th power, Right, so I have something to the 5th power. Then r prime of theta would be 5 times something to the 4th power times the derivative with respect to theta of that something. All right, so let's fill in the somethings, the boxes. That's the tangent of 4 theta. And then that's, again, the tangent of 4 theta. But now, if we think of how we would calculate the derivative with respect to theta of tangent 4 theta, I'm again going to have to use a chain. So now I have, again, a composite function. Let's think of this as maybe a triangle. Let's think of instead of a box, let's think of that 4 theta as being in a triangle. All right, so what do we have so far? We have 5 times tangent of 4 theta to the 4th power. Then the derivative of the tangent function is secant square. So I'd have secant square triangle times derivative with respect to theta of triangle. And again, what's in the triangle is 4 theta. All right, so what do we have? We have 5 tangent 4 theta, all raised to the 4th power, secant square of 4 theta, and then the derivative with respect to theta of 4 theta is simply 4. All right, and we can clean this up a little bit. 5 times 4, right, this is all being multiplied. So I have r prime of theta is then 20, let's see, 20 tangent 4th of 4 theta times secant square of 4 theta. Okay, so we've got to be careful. If we have a composite function where there's multiple compositions, for each composition, we're going to have to add on a chain, right? We're going to have to add on another link to the chain. Okay, so that's something to be careful of. Multiple compositions, multiple chains. All right, so these were the, in a sense, the straightforward exercises applying the chain rule. So I'm going to stop this video here, and in the next video we're going to also look at the chain rule, but with more complicated exercises and a couple applications. All right, so I'll see you there.